Good morning, everyone. So welcome to my YouTube channel, Maths. So today we are going to see 29th lecture on Riemann integration. Today we will study second mean value theorem for Riemann integration. So second mean value theorem for Riemann integration. Okay. So let's see what is its statement. Let G belongs to R, A, B, okay, and F close interval A, B to R be a monotone function, then there exists J belongs to closed interval A, B such that integral A to B fx gx dx is equal to f A to J gx dx plus f B J to B gx dx. Let's see its proof, how it will work. Okay. Proof. Okay. So F closed interval A, B to R is a monotone function. And we know that monotone functions are Riemann integrable. So this implies F belongs to R, A, B. Okay. Now, since F and G both belongs to R, A, B, we get their product F, G also belongs to R, A, B. Okay. That is also true. That is why we can talk about integration of F, G. Okay. So, F is monotone function. So F closed interval A, B to R is monotone. This implies either F is monotone increasing. First case is either monotone function is monotone decreasing. First case is F is monotone decreasing, or F is monotonically, okay, monotonically decreasing or monotonically increasing. Okay. So we are taking first case. F is monotonically increasing. Okay. monotonically increasing. So if, we are taking first case monotonically decreasing. First case we are taking monotonically decreasing. First case we are taking f is monotonically decreasing. In this case we will prove the theorem first. Okay. So put gx is equal to fx minus fb. Then this implies g close interval. So we will put phi x. We will phi x. We put phi x. Phi x. Then phi x close interval ab to r is positive, non-negative, monotonically decreasing. Monotonically decreasing. Okay. Monotonically decreasing. Now, by Bonnet's theorem, for Riemann integration. For this C Riemann integration. Lecture 28. You see, we get what we get. We get there exists xi belongs to closed interval AB such that A to B phi G, A to G phi X GX phi X GX TX is equal to phi A to J GX DX. Now you put the value of phi x here. So what is the value of phi x? That is fx minus fb gx dx, and phi is both fa minus fb. This integration A to J gx dx. Now open this. What you will get? A to B fx dx, and this is fa, because this will be fb. Sorry, this will be fb. fb A to B gx dx, and what will be this? fa A to J gx dx minus fb A to J gx dx. Okay. Now arrange these integrations. Okay. So this is equal to A to B fx dx. Okay, you take this part here on right. A to J gx dx and take fb common outside. So this is a to b gx dx minus a to j gx dx. Now what is this? You can break your integral a to b, a to j and j to b. Then what will be remain here? After solving it, what you will get here? You can break the integration. So it will be j b gx dx. Okay. Outside is fb. It will remain as it is. Plus integration a to b, a to j gx dx fa is equal to a to b fx gx dx. Okay. So here is gx, sorry. It is typo. This is gx dx. Okay. So this theorem is proved. So this implies this is proved. When your function f is monotonically increasing, the theorem is proved. Okay. So we have proved the theorem. Now second case is f is monotonically. So in previous case one we have proved if f is monotonically decreasing, then the theorem holds. Now we are taking another case, f is monotonically increasing. Monotonically increasing. Now this is the second case. First case was monotonically decreasing. Okay. Now we are taking case f is monotonically increasing. Now f close interval a b to r. So if f is monotonically increasing, we put phi x is equal to minus fx. Then phi close interval a b to r is monotonically decreasing. By case first, we have there exists j belongs to closed interval a b. Okay. Such that a to b phi f gx is equal to phi a to j gx dx plus phi b j to b gx dx. Okay. Now what is phi x? Phi x is nothing but fx. So this implies you put the value of this is minus fx, this is gx, this is dx here. Okay. Dx is equal to minus fa a to j gx dx. And what is this? Minus fb j to b gx dx. Now take minus outside. So take minus outside. It will be minus a to b fx gx dx. You take minus common, fa a to j gx dx plus f d xi to b gx dx. Now multiplying both the side by -1. Multiplying both the sides by -1. We get a to b fx gx dx is equal to fa a to xi gx dx plus fb xi to b gx dx. Okay, so this is proved. So we have proved the theorem in both the cases. Hence a to b fx gx dx is equal to fa into xi gx dx plus phi b xi to b gx dx. Okay, so theorem is proved finally. Okay, now we are going to prove a particular case of second mean value theorem. Okay, particular case of the second mean value theorem for Riemann integration. Okay, let f comma g let f close interval a b to r be a monotone function and f dash g close interval a b to r be continuous function, then this is particular case, that is why I'm underlining it. Then there exists xi belongs to closed interval a b such that a to b fx gx dx is equal to fa a to xi gx dx plus fb xi to b gx dx. Let's prove. Put gx is equal to a to x, a to x a to x gt dt. Okay. Then by first fundamental theorem of integral calculus, we have g dash x is equal to capital is equal to small g for all x belongs to closed interval a b. Okay. X belongs to closed interval. Now also note that GA is equal to A to A, G to DT is actually 0. Okay. Now A to B fx gx is equal to A to B fx g dash f dx. Okay. Now by integration by parts, first function, the integration of second function g dash gx A to B minus gx f dash x dx. Okay. This one. F dash. Now what is this? What is this? This is f b g b minus f a g a minus A to B gx f dash x dx. But this is 0 because g is 0, so it will become fb gb because ga is 0. A to B gx f dash x dx. Okay. So what we have? We have this one, A to B fx gx dx. That's it. This equation number 1. Now f is monotone. So this implies either f is monotonically increasing or decreasing. Monotone increasing or decreasing. So this implies once a function is differentiable, if function is monotonically increasing, then its derivative is okay. monotonically decreasing and derivative exists, then derivative will be non-negative. Okay. So this implies that f dash does not change its sign on closed interval AB. Okay. Therefore, by generalized first mean value theorem, we have what we have here. Capital G function is continuous. We have here exists Xi belongs to closed interval AB such that A to B Gx f dash x dx is nothing but dx is nothing but G Xi. Okay, G Xi A to B f dash x dx. But what will be this? This will be by second fundamental theorem. This will be f x A to B. What will be this? I'm writing directly. So it will be fb minus fa by second fundamental theorem of integral calculus. By second fundamental theorem of integral calculus. Okay. So what we have actually, now we put the value of, so this implies A to B Gx phi dash x dx. What is the value of G Xi? This is nothing but A to Xi gt. Okay, A to y gt. And this is what? This is fb minus fa. Okay. So what you can write in place of t, you can take x also. In place of g, in place of t, you can take x also. Okay. So this is what you can write fb minus fa here. A to Xi gx dx. So this is A to B Gx f dash x dx. So this is equal to this. Okay. So from 1 and 2, we have from 1 and 2, we have what we have a to b gx, sorry, a to b fx gx dx is equal to, what was this? This was fg gd. Okay. And now this is fb minus fa a to b gx dx. dx. Okay. So this is dx. Now okay. So after this actually, okay. So for time you do not put anything here. Okay? So do not put something here. Okay. So we call it again. So do not put anything here. We will put it later. Okay. So write it. So write it. G J. So we write it G J. Okay. G J. So this implies. So we are calling this equation G J F B minus F B. This is equation number 2. Okay. Now from 1 and 2, what we have? So write it here. This is G J F B minus F B. Okay. Now what is this? You can write it. So F B G B minus G J F B plus G J F A. Okay. This is F A. Write this here. FAGJ. Okay. Now you can take FB outside. You can take FB outside. What is this? FB outside you are taking. This is GB. What was this actually? This was nothing but, this was not small g, it was capital G. So let me check it again. This was capital GB. Okay. So sorry for that. I'm writing it. Capital G it is. This is capital G. This is what. So I am taking FP outside, then it will be capital GB minus G J. Okay. Now put the value of G J. Now put the value of G J. To J G X dx. Okay. dx plus FB. What is this? This is A to B Gx dx minus what is this? A to J Gx dx. Now after solving this, what you will get? You will get J to B Gx dx FB. This is okay plus FA A to J Gx dx. Okay. So this is J here. This is G. So this is G and this is J. And this is A to B Fx Gx dx. Okay. So this is proof. So this is proof. So today's lecture up to this. If you have any program related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. We will see you in next lecture. Thank you very much.